This next lecture is on matter itself. So chemistry is the study of matter, and there's a lot of matter, as we talked about, a lot of different types of matter in the whole world. So where do you even start? Well, what we do is we start by classifying matter by things that we can observe, because we are going to take those observations and use what we observe at what we call the macro scale, which is what we can see, to make predictions about what's happening at the micro scale, which includes like the atom level that we can't see. Lots of different ways that we can classify them, but here are the ones that you need to know, what we're going to need to focus on here. So first, we can classify by state. So state of matter, we're talking about, is this a solid? Is this a liquid? Or is this a gas? Right? Now, these have very specific definitions. A solid is something which has a specific shape and volume. That's how we're going to define that. So it cannot be compressed to take up, for instance, less space. And it's going to stay in its shape, right? So the mug that's on your desk, that is a solid. Whereas a liquid is something which has a specific volume. You can't really compress it, but there's not a specific shape. It's going to flow and take the shape of whatever container that it's in. So the water that's in your mug on your desk is a liquid. And you can see it can kind of flow inside of that cup. And then your gas here then has no specific shape or volume. So gas is going to flow like a liquid would, but in addition to that, it can expand to fill the shape of the room, right? So if you're working in a room with several other people and one of those people lights off a stink bomb, and then that gas from the stink bomb is going to expand to fill the room, and everybody in the room is going to smell it, even though it's a gas, right? And it was just put in one place. And in fact, the people down the hall and around the corner, and probably everybody on that same level of that building, is going to smell it. So that's what we're looking at for these. Now, this might seem obvious to us, and it's obvious primarily because we grew up in a culture that recognizes this. But if you went back, 2,000 years to the ancient Greeks, this was not necessarily obvious to them. But as I was saying, it's not as obvious as it might sound, because for thousands of years, this was not something that was well understood. And in fact, I think it was Aristotle who back then, looked at the fact, made this observation that some things are solid and some things are fluid, and said essentially, okay, well, that means that everything's made up of just 4 elements, and there's a solid element, and everything that's solid is primarily made up of this solid element. And then there's a liquid element, we're going to call the solid element earth, and then there's a liquid element, water, and everything that's liquid is made up primarily of this liquid element. And then there's a kind of a vaporous element, we'll say air, and then we might say that there's another element like fire, and that everything is just a combination of those, right? So a solid like gold is mostly earth because it's a solid, but maybe it's got a little extra fire in it because it's golden, right? And a liquid like blood is really primarily water, but maybe it has some extra like fire and earth elements in it. And all we have to do if somebody's sick is to like balance those elements. Maybe you need a little extra fire, maybe you need a little less blood, maybe you need a little extra earth in your blood, or something like that. And it's very optimistic because it's so simple, but also you could just solve any problem by just adding a little bit of this and taking away a little bit of that, right? So if you have lead, well, now all that remains is to try to figure out, if you want gold, is to figure out how much more fire you've got to put in that lead to make it turn into gold. And then you'll be rich, right? So this is and Aristotle was a pretty smart guy, but he still didn't kind of make this connection. And I want to kind of emphasize to you, one of the reasons that this is the case is that the Greek scholars were, while being hugely influential philosophers, they were not a hands-on kind of people. It was a slave society, so anybody that did work that you and I would consider like an experiment, that would have been a slave, right? And these philosophers kind of had this idea that if I just sit around and think about something for long enough and talk it out with my other smart friends who think about it for long enough, then we can come to a knowledge of truth by doing that, right? And so there would have never been an idea of like, well, gosh, that's an interesting hypothesis, Aristotle. Let's go test it out and see what we can find, right? Nobody did that. And as a result, we're stuck, for 2,000 years with this, now we might call it a silly idea of, there only being 4 elements, and they're earth, air, fire, and water. And that's what it is, right? And it was the 1800s really before the atomic theory came back into vogue, and we started searching for elements and characterizing them and discovering the fact that our world is actually made up of 100 different elements. Anyways, so we classify this, and an obvious way for us to see it this day is to look at water. It's ubiquitous. We see it everywhere. We see solid water as ice. And if you leave that out on your countertop, it's going to melt into liquid water, which is what we just normally call it as water, because at natural, room temperature, water is a liquid. But if you put that water in a pan, for instance, if I'm going to cook some pasta, then it will start to boil if I apply heat, and it will form a gaseous water. It's still water. All of these things still are actually water. It's not water becoming something different. It's just water vapor versus solid water versus liquid water. You can collect that water on the underside of your lid, and you can see that water turn into a vapor, and then it can recondensed there, right? You see when you take a shower, that water evaporates and then fills the room with steam, and then at every surface that it hits, it starts to condense on, and you'll see water droplets on your mirror and water droplets on your windows and water droplets on your glasses, right? As it's the water in the air condenses. Any questions on classification by state? Nope, no questions? Okay. Well, the next thing we're going to talk about is this idea that I told you. We can use this observation of what we see at the macro scale to predict what's going on at the micro scale. And so what we predict with the solid is that whatever the smallest particles are here, and I'm not even talking about atoms yet, I'm just saying whatever the smallest particles are in this solid, those particles must be packed together really tightly in fixed locations. Because I can't compress it, I can't make it take up less space. It has a very specific volume, right? And they don't move, so they must be kind of stuck to one another. If you can kind of imagine, if you've ever been usually you'll see this in different countries that are much more populous than what we've got, but you'll hear people talk about being on a bus in another country where they it is just so packed and they just can't even move. That somebody could come steal their wallet and all you could do is just protest. Hey, get back here, that's my wallet. Hey, I can't go anywhere, right? You're just stuck. So that's the smallest particles in a solid. We think that they're stuck because they don't move and they are close to one another because we can't compress that any further. Whereas a liquid, because we can't compress it further, we understand that those particles are really close to one another still. But because the liquid itself flows, then we understand that individual particles can flow past one another. They have movement ability there. And so as a result, that's why the bulk, the aggregate substance flows because they do have a little bit of movement ability there. But they're still really stuck really close to one another. You could think of that like you're getting on a really crowded elevator, right? And there's a whole bunch of people there. And you can kind of, if you need to get off, right, you can kind of turn sideways and apologize and slide past people, right? But you're still pretty crowded, but you can still move. Now a gas, because it has no specific shape or volume, we can predict that those individual particles are really far apart. Because then if you put them in a larger chamber, then they have no problem expanding to fill the space, right? Or you could compress them into smaller chamber because you can just reduce the amount of empty space between them. And that's how you might get a cylinder full of oxygen gas, for instance. And then of course, because they have no specific shape, there's going to be no specific volume. They're just going to bounce off the walls of whatever room they're at. We look at these individual particles as being very far apart and just moving, zipping all over the place. All right, so that's one method. Next, we can classify by properties. So let me put this right here. And there's multiple kind of properties that we could use. First, we're going to break this down to physical Whoops. Oh, for crying out loud. Physical versus chemical. So, for our definition here, a physical property, it's going to bug me that it's not in line there. Okay. Physical property is something which, hang on just a second. A physical property is something which can be measured without changing the identity or the composition of a substance. Changing. Whereas chemical, in contrast, is going to describe how a substance may change from one form to another. Right? So if you are measuring a chemical property, because chemical properties describe how it changes, the thing has to change in order for you to measure it, if that makes sense. So I'm just going to give us a couple examples, and I want you guys to help me determine if this sounds like a physical or a chemical property, okay? And you're going to do that in the chat window here. And if you're watching this hours later, I want you to think about it and come up with some of your own ideas here. But let's say, for instance, the color of a property. Would that be a physical property or a chemical property? Excellent. I see one vote for physical. So color, physical. Because you can look at the color of milk and say, that's white milk. And it doesn't change what the milk is when you do that. Right? Excellent. Oh, you all got it. Excellent. Okay, what about mass? How much something weighs? Excellent. I've got 3 votes for physical here. That's physical, right? Because when you step on the scale and weigh yourself, you don't like cease to be you, right? Or if you're weighing out sugar or flour for a recipe, it doesn't stop being sugar or flour. You're measuring how much it weighs, but it doesn't change what it is. Okay, what about if something is flammable? Excellent. You guys are all saying chemical. Excellent. That's right. How can you tell if something is flammable? Yeah, you got it. Comments. You try to light it on fire, and if it burns, then it's flammable, right? It's not like color. You can look at it and say, here's what the color is. It's not like mass. You can stick it on a scale. If you want to know something burns, you have to try to burn it. And if in fact it does burn, then that process of burning changes that substance to something else, right? If you burn a newspaper, what's left over is no longer newspaper. All right, excellent. What about if something is edible? Excellent. Yeah, chemical. You got it. Edible. How can you tell if something is edible? Yeah, you have to eat it and then find out if you die or not, right? That's how you tell if something is edible. Just like the flammable, there's not really another way to determine that other than trying, other than, well, I mean, I suppose if you, depending on your social status in the environment which you have to figure out whether something's edible or not, you could get somebody else to eat it and determine if it was edible. But there's not another way. And so, and after you eat something, it undergoes changes, and when it comes out the other end, it is not the same thing, right? You eat an apple, it does not come out an apple. So that's that. Okay, what about if something is, what about the odor of something? How something smells. Yeah, I think physical is a good one here. Oh, physical, hello, odor. Because the chocolate chip cookies don't cease being chocolate chip cookies just because you smelled them. Now, several of you are noting that you could kind of go do both on this. And I think that is a fair thing, because the fact is the cookies themselves don't change, but the odor molecules that come from the cookies have actually left the cookies, right? And what you're smelling isn't the cookies anymore. It's that odor molecule that left the cookie and floated through the air and has lodged in your nose and caused kind of a change in, it lodged into that receptor and sent a signal to your brain that you're smelling chocolate chip cookie. And so you might look at that lodging in your receptor and having left the cookie, as there's kind of a chemical change. But the identity of that molecule actually doesn't change. And then it does leave your nose at some point, because if it didn't, then your receptors would never be able to smell again, right? And so there's kind of an argument made to be both. What I don't want you to come away from this is to say the world is black and white, but I love seeing these, kind of, you might call it a fringe case, or understanding better what's going on here. Okay, what about volume? Oh, somebody also mentioned smelling an individual ingredients of a cookie is different than smelling the cookie. Although you could make the argument that the individual ingredients taken together is what makes the cookie the cookie. This is getting very philosophical. Who was it that said there was no chemistry in philosophy? I suppose that's philosophy in the chemistry. All right, volume, you guys said. Volume. So volume, like mass, how much space something takes up, that's physical. You can measure a cup of milk without changing the fact that it's milk, right? What about melting point? Oh, that's tricky. I've got 5 votes for chemical and 1 vote for physical. It is physical. Because even though the state changes, right? Even though melting, you're going to go from a solid to a liquid, the fundamental identity or composition of those individual particles doesn't change, right? So the melting point says, here's the temperature at which this transition occurs. So here's 0 degrees Celsius, for instance, is the temperature at which solid ice melts into liquid water. But the solid ice is made of water molecules and the liquid water is made of water molecules. So the identity or composition did not change. Does that make sense? Might feel a little bit tricky. So there is a change that occurs, but it's not a change in the substance identity. It's just a change in state. But these seem like such, I mean, you can kind of see why it took us 2,000 years to figure out that they weren't changed, because it does seem like such a big change. But you're not changing identity, you're just changing the state of matter there. Okay, what about radioactivity? Radioactivity is, I'm going to put it over here. Radioactivity is, you could say chemical, because in the process, like as you measure radioactivity, then essentially what you have is you have some sort of substance here, which is radioactive, and it's radioactive because it's sending out maybe alpha particles or beta particles or gamma particles. It's sending out radiation. Radiation. This is why I type and don't use my mouse. And you're using some sort of a detector here, detector, to detect that radiation. Does that make sense? The source of a radiation is an atom which has released that radiation because it has just changed from one atom to a different atom, essentially. Has changed from one form to a different form. So a chemical change has occurred, and that's what the source of the radiation is. So that's why I would say chemical. But at the same time, you'll note that the bulk of this isn't really changed, right? So this is almost like odor, where the detector is like your nose, right? And most of that cookie remains the same, but there's just a little bit of it that manages to escape and hit you. Does that make sense? So I can see, you could maybe kind of put it over here. Does that, are you guys with me here? It could be, you could make an argument either way. Just as with odor, you can make an argument either way. Like the cookie doesn't cease to be a cookie because you smelled it. And the lump of uranium doesn't cease to be a lump of uranium just because you detected radiation. But at the same time, the process by which our nose processes odor, right? Now that we kind of understand these processes better, it's definitely a chemical one where a chemical molecule has left the cookie and has entered your nose and caused a chemical bond, even a temporary one, with the receptors in your nose, right? Or in the radioactivity, some of the atoms, what you're measuring there is the fact that some of those atoms have actually changed within that lump. Not all of them, but some of them. So it's a little bit tricky. So that is that. All right. How do you guys feel about physical versus chemical? I promise that I will never ask you one that is tricky like this. And if I did, then I would allow you to argue for it, right? If I marked you wrong. I learned early on to ask very clear questions. Okay. All right. If we feel good about that, then let's look at the next kind of properties we could use. Classify by properties. Whoops, made those Y's. Continued here. And we're going to say, now we have intensive versus extensive. All right. So an intensive property is one which does not depend on the quantity of a substance, whereas extensive is something that does depend on quantity, right? So, and again, like the physical versus chemical, there'll be some that are clearly one or the other and some that seem like they're a little bit in between, and we can work through those and see what we can find. So I'm going to toss them out here, and I want you guys to toss guesses at me as to what you think that they are. So what about, let's see, we did color over here. Would color be intensive or extensive? Ooh, now I have 3 votes for intensive and 2 votes for extensive. Ooh, that's tricky. Okay, so color, we have to ask, okay, milk is a great example. Everybody knows what milk looks like. Is the milk white if you have a cup of milk versus a gallon of milk? These are 2 different quantities. Does that change does the color change depending on if I have a cup or a gallon? The color does not change. That's correct. And so that would make it intensive. Color is intensive because it doesn't matter how much you have, it's going to have the same color. You might have a larger amount of white, but it would still all be white, right? Okay, what about mass we've got here? Mass is extensive. If I have a gallon of milk, it's going to weigh more than a cup of milk. Yes, all right, you guys got that. We're on the same page here. Okay, what about volume? Extensive, yep. Obviously a gallon is larger than a cup. So volume goes here. What about melting point? Intensive. That's right. The freezing point or melting point of water is always 0 degrees Celsius. Doesn't matter if you're talking about an ice cube or if you're talking about the snow on your roof. It melts at 0 degrees Celsius, which is always a little bit confusing to some students, because you'll note that in terms of the energy required to melt the water, that would be extensive, right? So even though they melt at the same temperature, if I have more of it, it's going to take more heat, right? So say heat required to, for instance, melt or boil, right? You can say the boiling point would also be intensive because just the temperature at which that happens doesn't change, but the energy required to make it happen, that would be extensive. Does that make sense? All right, if it makes sense to at least one of you, then I'll just keep going. If not, you have to speak or forever hold your peace, right? All right, odor, what do you guys think? Intensive or extensive? Oh, I love it. I've got a couple votes for intensive, 1 vote for extensive, and 1 person who says that will be both. Right? And I think a good argument could be made to say, yeah, it could potentially be both. So if you're smelling a chocolate chip cookie, or if you smell a whole batch of chocolate chip cookies, that's intensive. They're going to smell the same, right? Your nose knows, oh, I smell cookies, right? But it's also true that the receptors in your nose, there's only so many of them, and there is a point at which your nose can be overloaded and you can't smell it anymore. This is a pretty well-known phenomenon. If you are surrounded by or exposed to a certain odor for a long period of time, then you just can't smell it. Like a person who has like really bad body odor, they really might not know. They really might not be able to smell it because it's just their nostril receptors are full, and once they're full, then you stop. Once the chemical gets lodged in there, unless it has a chance to leave to let something else come back in, you're not going to smell it again. So Like, question, like when they have coffee beans when testing perfumes. I've never heard of this, but it sounds like a way to kind of clear out your nose, like a cleanse the palate kind of a thing. That's true. And people who work in environments with lots of smells, like if you're working in a factory that has, you might lose the ability to smell that thing altogether. You might lose the ability to smell altogether. So in terms of small quantities, it's intensive, but if you overload it, you could argue that odor is extensive. I'm going to put this in the middle. We don't often think about that because it doesn't often happen to us, but when it does, it's really interesting. And if it's happened to you, then you know, some people have permanently lost the ability to smell because of it. Okay, what about radioactivity? All right, I've got 5 votes for extensive and 1 for intensive here. I'm gonna say, going back to our picture, the fact that it is radioactive, that does not depend on the quantity. But if you're talking about the radiation dose that you are receiving, that is totally extensive, right? The more of the radioactive substance you have, the higher the dose that you're going to receive, versus the fact that it is radioactive at all or not doesn't depend on quantity. Does that make sense? You're going to want to be really careful to and very precise to make sure you're answering specifically the question that we're talking about. What about flammable? All right, I've got 3 votes for intensive and 1 for extensive. So yeah, it's going to be here. It's the same story as radioactivity. If something is flammable, it just says, do I burn or not? And that doesn't depend on quantity, right? If you're asking if paper burns, a tiny bit of paper burns, a lot of paper burns, it's all flammable. But if you're asking yourself like how much heat is released while burning, that would be extensive, right? Because a house burning is going to release a lot more heat than a matchstick burning. Is that, you guys with me? Very similar to the radiation. Okay, what about edible? Okay, excellent. I've got a lot of people saying intensive, but a few people noticing that it could be both. Just like odor, it's like generally speaking, water's edible, but if you drink too much of it too fast, then it can kill you, right? It's the dose makes the poison, right? So are grapes edible? Yes. If you're eating, normal amounts. But if you ate, gallons and gallons of grapes, like if you could, then that could actually not be edible. That might actually hurt you. You guys with me? Could be both. Mostly intensive for like our normal environmental exposure kind of a thing. Excellent. Okay. All right. So the properties here are used to help us determine what we really, really want to know. And that is, we want to classify things by composition. What are things actually made out of? I don't want to lose this, so I'm just going to zoom out and I'm going to make it bigger. Stop you. Okay. I'm going to continue this down here so I can go back and refer to this. Because we're studying matter, what we really want to know, what's it made out of? Why does it act the way it does? We really want to classify it by composition. And we're going to use those properties to help us. Oh, this is great. Somebody asked a question. Sorry, I moved on a little bit too quickly. On edible, is it the same for like French fries? Yes, it's the same for French fries. Some French fries are edible, and too many French fries can hurt you. Some people would tell you that even just a few French fries can hurt you in terms of like long-term effects. But that's a study that I haven't seen a 30-year replication on. So 30 years of work replicating that. So I couldn't say for sure. But it's the same for pretty much all food and drink, right? Occasionally you'll see cases where somebody drowned by drinking too much water. Sometimes it happens to little babies because they should never be given water, actually. Because again, while small amounts are fine, larger amounts are not, and little babies are much more susceptible to that. Sometimes you'll see it in a youth who is being punished for something by inexpert parents who forced them to drink a lot of water and they died. I can't imagine, I mean, you can imagine, but who knows, a case where a person would just order so many French fries that they just sat down and ate them until they died. But it could happen, theoretically, hypothetically. You would probably get sick before you got to that point. Same for like alcohol, which is poisonous, but usually you pass out before you drink so much you die. Same thing. Excellent question. Okay, sorry. Back to classification by composition. And here we're going to separate this into two categories. We're going to say mixtures, which have just kind of two or more different things just occupying the same space, and pure substances, right? So just as like kind of a picture of what's going on here, if you zoomed in on a mixture, you would see the smallest particles in those mixtures would be different things. Doesn't really matter whether this is a solid or a liquid or a gas. You're just seeing that it has different things inside it in terms of fundamental identity. Whereas a pure substance, you're going to zoom in and you're going to see that it's all the same thing in terms of fundamental identity, right? And if we can classify things this way, then hopefully we can start identifying what makes one pure substance differ from another pure substance, right? And if we can, our first goal is to try to separate mixtures into individual pure substances so we can start characterizing them. Let's say you're a 19th century chemist. That's our goal. All right, so a mixture, by definition, here we go. Our definition of a mixture is it is a substance which can be, I'll just say can be separated into individual component parts by physical means. And each component part retains its original properties. And by original properties, I mean these properties here. Okay? So for instance, if I have if I've got a cup of coffee in front of me, and it's a mixture that contains, if you looked into it, you zoomed into it, it contains some water bits and some, we'll call them coffee bits, whatever it is that makes it coffee, and maybe some cream bits, right? And maybe some sugar bits. Each of those component parts would retain their original properties. So the water is clear as a color, but the coffee bits are brown as a color, dark brown, and the cream bits are white as a color. And so when you mix those together, you end up with kind of a light brown mixture. not because it's chemically changed into something else, but because you're combining dark brown with white and they're kind of dispersed evenly. And so on balance, you get that light brown color. Does that make sense? Okay. A pure substance, in contrast, they're going to have a, they cannot be separated by physical means, right? We're going to have a constant composition. And this is, here's my little picture of constant composition. You got the same thing here. And I'm going to put this distinct properties. All right. Let's look at a couple examples and then we can elaborate more on what this means here. So just as a couple examples, would you call ice cream a mixture or a pure substance? Mixture. Okay, I'm going to put this here, vanilla ice cream. All right, would you call water a mixture or a pure substance? Pure substance, good, okay. Okay, would you call vodka a mixture or a pure substance? Oh, that's tricky. Okay, I'm getting like half and half here. But it is, it's actually a mixture. It's pretty, it's pretty much just water and alcohol. So it only has 2 ingredients essentially, but it really is just water and alcohol. And it does have both of those in there. It can have some other things like flavorings in there. There might be some leftover flavors from the thing that it was distilled from, but it's just going to be mostly alcohol, but it's got some water in there. So vodka, because it's got 2 different things in there. Okay, what about gold? Pure substance. Excellent. Gold, pure substance. What about salt? Pure substance. Okay. What about granite? Like the rock. Excellent. Granite mixture. What about chlorine? I need to clarify, because in our local language, chlorine could mean something like chlorine bleach, which would be a mixture, or it could be the element chlorine, which would be a pure substance. I did mean the element chlorine. Chlorine element. Whereas chlorine bleach, I'll put this over here. Put it over here. Okay, someone asked, how can salt be pure? And this is a good question that deserves some discussion. So what we find when we start separating these is that we have 2 types of pure substances and 2 types of mixtures as well. So we'll put this in purple. All right. We have 2 types, pure substances. we have elements, which are literally like the smallest particle is an atom of this thing, and you can't actually get anything smaller than that resembles matter. But then you also have compounds, which are elements that have been combined chemically. Because they've been combined chemically, they can't be separated by physical means. They would have to be separated by chemical means. They still could be separated and they would form elements, okay? And so to elaborate on that, if we were to separate this here, we would find that, for instance, chlorine, elemental chlorine goes here. Or is in red. Obviously, because I told you it was elemental. Element number 17. What about water? Would it be an element or a compound? Compound. Great. And if you didn't know that, that's fine. That's what we're learning today. But I thought you might know it, so that's why. That's why. If you guys want to annotate and write it out, I'm totally happy to let you do it. Just ask me. But if I get it like a random pop-up, I'll assume that you just clicked on something on accident and I'll just dismiss it. Okay, so water is a compound because it contains, H is a symbol for hydrogen as an element. It contains 2 of those, and O is a symbol for oxygen. So the compound water is a molecule which contains 2 hydrogen atoms and 1 oxygen atom in it. So that's why it's got the symbol H2O for water. Okay, what about gold? Is that an element or a compound? Element, yep. Excellent. And salt, is that an element or a compound? It's a compound. Okay. Anybody know what the formula for salt is? Yeah, you got it. Salt is a compound that contains 1 sodium atom and 1 chlorine atom. So it's a ratio of 1 to 1 at its like smallest kind of nuclear piece, you might call it. Okay, so again, these do contain they can contain more than 1 element, but they cannot be separated by physical means. If you want to split water, you're going to have to do some sort of a chemical process, right? Like that's described here, something that's going to change from one form to another. Okay, so in contrast, we've got mixtures over here, and we find that we've got different kinds of mixtures. That is to say, some which are more obvious as mixtures and some which are less obvious as mixtures. So the obvious mixtures are the obvious ones are heterogeneous, and the less obvious ones are homogeneous. And the heterogeneous just means that you can see the individual parts, like with the naked eye. And the homogeneous means it's kind of mixed together. You can't really tell by the naked eye that it's a mixture because it doesn't necessarily look like multiple things, if that makes sense. So like heterogeneous are not uniform throughout, the homogeneous appear to be uniform throughout. So based on that, would granite be a heterogeneous mixture or a homogeneous mixture? Hetero, right? Because you just look at it and you can see little black pieces and little white pieces and little brown pieces, and you're like, oh, I see different things in there, right? There must be something that's fundamentally different about the black piece and the white piece and the brown piece that makes them different. Okay, what about vanilla ice cream? No, excellent. I've got 6 votes for homogeneous. Nobody's voting. 7 votes for homogeneous. Nobody says heterogeneous. What about vanilla ice cream with the little tiny vanilla bean bits in it? Those little black bits that you can see. I mean, it depends. Is it vanilla? Is it like fresh market plain vanilla ice cream, or is it some fancy vanilla bean ice cream, right? Yeah. So I'd have to be specific. And again, I wouldn't ask you this on the test question because it's a little bit tricky. But your experience tends to say homogeneous, and that's okay. I'll put it here. Ice cream. All right. What about vodka? Somebody asked, what about cookies and cream ice cream? You guys are right here. Vodka's homogeneous. Cookies and cream ice cream. Somebody asked, so we can help answer that question. It's like vanilla with little bits of Oreo cookie in it, right? Yeah, that would be heterogeneous because you can see the bits of cookie. Oh, I'm sorry. You guys all said homogeneous, and I don't know why. It's definitely homogeneous. I don't know why. My brain was on to cookies and cream ice cream. That's why. Okay. Because you can see the little cookies. Okay. What about chlorine bleach? Homogeneous, yeah. Excellent. Too much talk about food. Well, I use food as an example just because it's something that's like so universal in terms of your experience. So it's great. What I want you guys to know about chemistry, one of the things I want you to know is that you know stuff about chemistry already. Whether this is your first chemistry class or your fifth chemistry class, there's stuff that you've experienced in your life that tells you something about chemistry. Ooh, here's a question. Would salad dressing be heterogeneous? What do you guys think? It depends. That's the answer. One answer for depends and one answer for yes. It depends on the salad dressing, right? If we're talking about like an standard oil and vinegar, shake it up, that's definitely heterogeneous, right? Because you're seeing the different layers of the liquid and the different stuff that's suspended in it, right? If you're talking about poppy seed, that's one of my favorites, poppy seed dressing. Definitely heterogeneous. But then if you're talking about Catalina dressing, some of these other ones appear to be pretty homogeneous. Now, sometimes, again, you're going to say it depends, right? Like vanilla ice cream, it depends if there's little bean bits in there. But something like, for instance, is air homogeneous? Like, according to your experience, my experience, all of our experience, we'd say, yeah, it's pretty homogeneous. Like, I don't see bits in my air here. But it depends on the sample size, right? The air in your bedroom is probably homogeneous. But if you're standing on the mountain peak and looking over the Salt Lake Valley in inversion season, you see a lot of air that does not look homogeneous. It's like layered, right? And you go, wow, I'm going to climb down off this mountain and breathe that. Delicious, right? So those are some things to kind of think about, right? Blood, homogeneous, heterogeneous, looks pretty homogeneous by the naked eye, but if you look at it under a microscope, it might start to look heterogeneous. So your sample size and what you're looking at it with does make a difference. But again, I'll try not to give you ones that are, like on an exam type setting, I wouldn't give you ones that were fringe cases or debatable. And if I did by accident, then I would let you debate me, okay? We'll go by that. Is that fair? Okay. All right. So let's talk about a little bit more about these. Now, I did note over here that pure substances have a constant composition. And that is in contrast over here. If pure substances have a constant composition, then mixtures over here, in contrast, they would have to have a variable composition, right? What do we mean by that? Well, what I mean by that is that gold, for instance, wherever I find it, if it's a sample of gold and if it's pure, it always has tiny gold atoms, nothing else. And all the gold atoms are the same, no matter whether I dug that gold out of a mine in Utah or whether I found that gold in a river in Zimbabwe. It's going to be the same, right? No matter where I get it, it's made out of the same thing. Compounds are the same, constant composition. Water, by definition, always has the tiniest particles, consist of 2 hydrogen atoms and 1 oxygen atom. If I zoom in and look at that, right? And it doesn't matter whether I got that pure water from a water reclamation plant in Magna or I isolated it from a glacier lake in the Alps. If it's water and if it's pure, the composition of those 2 samples of water will be identical. Does that make sense? Okay. In contrast, let's look at, for instance, vanilla ice cream. I can get vanilla ice cream from the grocery store, is like the Western Family brand, whatever they call it these days. I can get vanilla ice cream from a gelato store in Italy. I can make vanilla ice cream at home. Would all of those vanilla ice cream samples have the exact same composition? That's right, they would be different, right? Not to say that one would be yucky and the others would be delicious, but that your different recipes, or some of them might include eggs, and some of them might have a higher cream percentage, and some of them might have added little vanilla bean bits, right? And other ones might have added a little bit of, extra sugar, or one of them might be sugar-free, right? And be using some sort of a sweetener alternative, but they would all be called vanilla ice cream, right? And when I say variable composition, I don't mean within a single sample, because we already just said within a single sample it's homogeneous, but I mean across all samples that you could ever find anywhere, right? I'm gonna write this down. Across all samples encountered and anywhere, right? Whereas this is constant composition, again, across all samples. No matter where I get that water from, it's the same. No matter where I get that vanilla from, they'll be slightly different in certain ways. Okay, so that's constant composition. And then the other thing we've got here is distinct properties. And this is in contrast to the mixtures where they retain original properties. Now, distinct properties is more useful or interesting for this part over here, right? Because we can kind of understand, okay, gold is gold and it has different properties from chlorine, because that's what makes gold gold, and that's what makes chlorine chlorine, and they, at the fundamental pieces, we have this fundamental pieces. But what makes the compound different from the mixture when they both could be said to have multiple, like a combination of atoms? And what makes it different is these distinct properties that come from the fact that they are bound together chemically. So if we look at salt as a great example of distinct properties, and we could say sodium is an element and so is chlorine. So we'll put this here, sodium and chlorine. And they have their own distinct physical and chemical properties, okay, that we can describe. For instance, sodium, I might need a little more space here. Spread this out. Okay. For instance, sodium is a metal, solid at room temperature. It's highly reactive with water. If you put it in water, it's going to bubble and foam and it might light on fire. So that's pretty cool. All right, chlorine is an element. I already listed it here. I don't know why I listed it again. Is a gas. At room temperature, it's green and it's toxic. It will kill you. You don't want to breathe that, right? So here we have a highly reactive metal and a toxic gas. These are fundamental properties of sodium and chlorine. And you would say, for instance, that sodium and chlorine, you would not say that either of them is edible, for instance, right? But when you combine them together like this to make sodium chloride, the compound, I have completely different properties. Completely different properties. Like, yes, it's a solid at room temperature, like sodium, unlike chlorine though, right? And additionally, it's not reactive with water. And additionally, hang on a second, I'm losing my, additionally, it's non-toxic in small amounts. In fact, it is required for a healthy organism. Well, it's true that in today's society, everybody gets way too much salt. That has not been historically true. And salt is historically been really valuable commodity, and entire cultures would grow around making it and exporting it and using it. The story goes that in Rome, the soldiers were paid in salt, like it was money, and that's where the term comes, like somebody's not worth their salt. It's also where the term salary comes from the term salt. So anyway, so it's required, and that's totally different from the sodium and the chlorine, right? If I just mix these two together as a heterogeneous mixture, like if I could do that, then what you would see is a cloud of green gas sitting over a lump of metal is what you would see in heterogeneous mixture. Now, you actually couldn't do that because they would start to react together almost immediately to make sodium chloride. And that reaction would light on fire. It's a pretty exothermic reaction. But you can see, hopefully you see how the properties of the salt are totally different than the properties of the sodium and the chlorine. Does that make sense? You with me? Excellent. Okay, so that's what we mean by distinct properties versus retain its original properties. Because here in my example of something like putting together a cup of coffee, the water, the coffee bits, the sugar, the cream, they all retain their original properties. And so they retain their original color, they retain their original, like I'm a liquid or I'm suspended in that liquid, all of that. Okay, so if we are a 19th century chemist and we're trying to learn what matter is made of, then we want to try, our next goal is to try to separate mixtures into individual pure substances so we can learn more about pure substances as like the fundamental units of matter. And the way that we're going to separate them is we're going to use physical properties, the physical means, to take them apart. Now in something like granite, it might mean I'm going to smash that into tiny bits, and then I'm going to start sorting all of the red bits into one pile and all of the black bits into another pile and all of the white bits into another pile. That's separating by physical means, right? But then if it's something like vodka, we might need to do something a little bit more. So let's talk about methods of separating mixtures. There's a few that I want you to know here. We've got distillation. This is how you're going to separate the alcohol from the water in vodka. Filtration. A quick Google search tells me that vodka is usually about 50% water, 50% alcohol, but it can be up to 95%. That's your variable composition for you. Centrifugation, chromatography, and adsorption. Okay. All right. So distillation is going to separate mixtures based on volatility, but basically boiling point. Filtration is going to separate things. Yeah, these are all methods of separating mixtures. Separate based on particle size. Here we go. Centrifugation. I'm going to separate based on density. Chromatography separates mixtures based on a huge range of things depending on what kind of chromatography you're doing. Talk about that a little bit more in a minute. Adsorption is going to separate based on reactivity. All right, so distillation separates usually volatile liquids from less volatile liquids, but you can also use it to separate liquids from solid, like for instance. And so what you're going to see with this, for instance, what does this look like? This is so nice to do this on the computer because I can just like Google a distillation apparatus and then show it to you. If you guys have ever watched like any TV with like a mad scientist, then you've seen a picture of a distillation apparatus, because this picture is like, this is how you know that they're a mad scientist, right? They'll stick it in here as like a, okay, it looks just like this. Do you see this? Or something similar to this. They might have a flame underneath here. In this example, they've got a water bath, but they might have a flame to heat this up. Here's your mixture. And the thing that has a lower boiling point is going to boil first, and it's going to travel up here as a gas that has no problems getting up here. This is plugged, it can't get out there. And it kind of expands to fill the container as the gas. And then here you've got some sort of condenser. It might just be an air condenser, it might be a water condenser. This is a jacketed water condenser that's shown. Basically surrounds this middle piece with cold water, but it's separated by the glass, right? So it's not exposing it to the water, just surrounding it. So it heats up, it boils, the gas expands, and it hits this point, and then it condenses back into a liquid because it's too cold. And then the liquid comes down here and drips into this other flask where you're collecting the pure distillate. And then this is open to the air. You have to have something open to the air, otherwise you're heating a closed system and it's going to explode. So that's open to the air, but you don't want to lose the gas that you generated here. And so that's why your condenser here is turning it back into a liquid so you can collect it. Does this apparatus look a little bit familiar to you guys? Like, have you seen something like that? So you can put in two liquids that have different boiling points. The more volatile liquid has a lower boiling point, which means it boils more easily, like at a lower temperature, right? This is how, for instance, you are going to separate alcohol from water, right? And you might say, well, why would I need to do that? And you might never need to do this. But in the history of alcohol, in the history of cultures, we find is every culture has a version of a fermented drink, depending on what fruits or grains grow where they are, right? So you can make rice wine, or you could make wine out of grapes, or you could make cider out of apples, or you could ferment potatoes, and you could ferment corn. Whatever you're making, you can make a fermented version of it. And when you ferment, you're producing alcohol, but the microorganisms that are doing that, as it turns out, alcohol's poisonous, and poisonous to those microorganisms as well. And so at some point during the fermentation process, you get enough alcohol in the system that those microorganisms die. And in a fermented drink like that, you can get maybe 12 to 18% alcohol maximum before you're killing off all of your microorganisms that are helping make alcohol. And then you might say, gosh, this is great. I like to get drunk off of this, but the fact of the matter is, if I made it out of potatoes, it might not taste very good. Making it out of grapes is great, no problem. Make it out of potatoes, I'm not so sure I really want to drink that. Or you might say, this is great, but I want something harder because my life just sucks right now. I don't know why, but for whatever reason, you might want something with a higher alcohol content. Actually, I'll tell you a great reason to do it, because alcohol makes a great fuel, but it doesn't burn very well when it's got a ton of water in it, right? It's not going to release a lot of heat because the water's going to absorb that heat. So if you wanted to make fuel, then that would be another reason to separate the alcohol from the water. Well, water's got a boiling point of 100 degrees Celsius. Ethanol alcohol has a boiling point of about 78 degrees Celsius. And so you just distill it, and the alcohol boils off more quickly, and you collect alcohol on the other end, and the water's left behind. Does that make sense? Let's see if I can find another picture I can just like post into this that would make sense. There are other ones, but nothing so fancy. Let's see if I can put this in here. Yeah, there we go. Simple distillation apparatus. In this case, this would be the thing that's being the mixture. This, they just put color. This isn't like real stuff happening. You'd put some sort of heat source underneath here, like a flame. It looks like it's set up for a flame here. And then this condenser, there's the jacketed condenser. Your water goes in here, water goes out here. You can see this glass thing in the middle. This is the path that the liquid travels. So they've made it a spiral so that there's a larger surface area for which it to condense before it drips down into here. Kind of fancy. Fancy thing here. By the way, if you want to distill alcohol because you want to make your own fuel, you do need a permit for the federal government to do that. Otherwise, it's a felony. And if you want to do it to drink, then you for sure need a permit, or else it's a felony, and it's actually even a little bit harder to get that permit. And if you're doing it for fuel but you drink it, then you're guilty of as well. So don't do that. Some of the problems that we discovered with the bootlegger moonshine whiskey era is that when you ferment it improperly or with the wrong ingredients and distill it improperly, you can collect a lot of methanol in your ethanol. And then you're drinking this drink that you think is alcohol, and it is alcohol either way, whether it's methanol or ethanol. But the ethanol is going to get you drunk, and then you'll pass out before you die, but the methanol is going to kill you, and if you don't die, then you're going to go blind first. And that's a problem. So that's why we don't recommend drinking bootleg or distilling your own bootleg whiskey, although it's technically possible. Moonshine, yeah. It's really not good for you. And actually, that's a little bit more relevant today, even with COVID-19 and the hand sanitizing shortage. So that a whole bunch of people started up hand sanitizer operations, and now a whole bunch of hand sanitizer brands have been recalled because they have unacceptable levels of methanol in them because of the improperly applied distillation process. So that's not just an old-timey story. It has relevance even today. Not that you're going to absorb it through your hands, and methanol will do a great job. So the hand sanitizer is probably still fine to use, but the FDA is still recalling them because they don't want anybody to drink them. Go figure. Yeah. Okay, so that's distillation. It's a little bit fancy. All right, but one other example of distillation, just distilled water. You've heard about distilled water. You can buy it in the store. And that's where you're going to take water and you're going to remove all of whatever comes out in your tap, right? Which is a mixture. It's mostly water, but it's got a little bit of calcium and a little bit of magnesium and maybe a little bit of chlorine and other stuff in it. And if you distill that water, then you can get just pure water on the other side and get rid of all that other stuff. Which, if, for instance, you're feeding plants in your house plants, you have to use, or you ought to use, distilled water. Otherwise, the ions, like the calcium and the magnesium, can build up to kind of unacceptable levels and kill your plants. There's another good example of distillation. Okay, sorry. Filtration, separate based on particle size. And this could be gases, it could be liquids, it could be solids, it could be whatever. A great example of filtration is when you make pasta, like you're making spaghetti noodles, and then you separate the extra large noodles from the really tiny water particles by pouring it into a colander. right? And your filter separated it. But you'll also see air filters in your car or in your furnace. Or you might have one in your bedroom that's going to separate like dust and pollen and stuff out of the air. Or for instance, you might see it in your classroom trying to filter, you can't filter maybe virus particles. I don't know if they're big enough. You could try to in a medical grade filter. It might be able to separate that. Something as simple as a face mask for COVID is separating out the larger particles, the larger droplets from a cough from smaller droplets, right? So that we can reduce the spread. So it's just a separation based on particle size. That's filtration. And gosh, the mask is a great example. There's a couple of really good videos online showing people putting on, pretty good masks and trying to, for instance, blow out a candle, or showing how much bacteria or junk you can get to grow in a petri dish if you cough through a face mask versus just coughing without one. So those can be helpful. Centrifugation is based on density. And so that is something that you guys as healthcare professionals might specifically see blood centrifuge, right? And so your blood has got a mixture. You've got some water in there. You've got some red blood cells in there. You've got some plasma, white blood cells in there. And you stick that in a centrifuge and you just spin it around really hard and it'll separate. You'll get like a solid pellet down at the bottom. And then you'll get a layer of like a red liquid. And then on top of that, you'll get a layer of a white liquid. And you'll see it's been separated based on density. Chromatography. Let's see. Chromatography. Super vague, right? Based on a huge range of things. But there's a lot of different types of chromatography. And the type of chromatography it is going to separate certain types of mixtures. So gas chromatography is going to separate things that are in the gas phase and does that via a special process. Whereas liquid chromatography is going to separate things that are in the liquid phase or in solution. And gel chromatography is going to separate things on a gel plate. And maybe based on size and charge kind of a thing. You get gel electrophoresis in biology, like as for instance. As a kid, you might have done an example of paper chromatography. I find that maybe 20 or 30% of my students have had experience with this. And you can do this at home. If you're interested, if you have kids, it's fun kind of to do with them. But essentially what it does is you take a little tiny piece of paper and you color a little dot on it, like maybe use markers. I'm just gonna pull this over from just a quick Wikipedia search. Take this paper, put a line on it, you put a little piece of maybe marker on there, and then you're gonna stick it inside of a chamber, like a glass, with a little bit of water on the bottom. Now, a little bit of water on the bottom means like down here, beneath where those little dots are. And paper, being paper, does what it does. It's going to absorb the water, and the water is going to move up the paper. And as it moves up the paper, it's going to grab this little dot and carry it along with it. And this is kind of you put a little glass dish on top so that it keeps it sealed. The vapor in the chamber helps it to move as well. But as it travels along the paper, then the individual components of the marker, the individual dyes that were used to make the marker that particular color, they travel along the paper. And based on how much those dyes are attracted to the cellulose on the paper versus how much they're attracted to the traveling medium of the water, they're going to travel at different distances. You can separate out the individual dyes. And this same kind of process can be used to separate out other things as well. But this is kind of a simple example of chromatography that can be done with just like household materials. And it's kind of fun to see. So chromatography, very general thing that says you're kind of separating things. And there's a lot of different types of chromatography out there. What I want you to know, your takeaway for this class, is that if you see the word chromatography, and it doesn't matter whether I'm saying gel chromatography or electrophoresis chromatography or liquid chromatography or gas chromatography, you know that I'm doing some sort of separation based on something. If that makes sense, that's all I want you to know. Questions on that one? How many of you guys have done this, by the way? Just as like a random question. I like it. There's a few people who said I have. Yeah, 4 or 5. Okay. And that's just of the people who are paying attention here too. So there's a few. Some of you have done electrophoresis. I was at the Bio 1610 lab. Some of you have done it with kids. It's kind of hard until you do it a couple times, just kind of like everything. It's not always intuitive the first time, to get the water level below the dot level, for instance. Or to make sure that, she's got a nice line here so that they all start at the same level and you can kind of see, all right, this O and this B are, I think this is brown and orange maybe, both contain this yellow component. If you don't put the dots in the same place, then these dots end up in different places and you can't tell what's inside of it really. Anyways, all right, so that's good. All right, so adsorption's our last one for this one. It's going to separate based on reactivity, and this is something that you and I might not have a lot of direct experience with. Often it will separate components from gas or liquid medium. So you're going to take the gas or liquid medium and run it across this adsorptive media, and it will pull out the reactive stuff from the gas or from the liquid. Now, adsorption is different from absorption. I'm not saying it wrong. It really is adsorption. A sponge absorbs things. Absorb with a B means that it takes it into itself. So a sponge absorbs water, whereas adsorption means it sticks to the surface of it. And the adsorption medium with a D usually has a very porous surface, so it looks a little bit like a sponge, but it's not like bringing it into itself. It's just making it stick on that surface. So our best example of adsorption is an activated carbon filter. And I'm even going to write this down. Activated carbon filter. And you'll see an activated carbon filter in, for instance, if you run a fish tank and you've got a filter going, it might go across an activated carbon filter, and that will help remove the ammonia as a reactive component from the water. The ammonia is a waste product from the fish, and if it builds up, it'll kill the fish. So you want that to adsorb onto the activated carbon filter. You might see it, you'll see it in like really high-end gas masks. For instance, if you were a firefighter and you were going to enter a burning building, you would put on your gas mask, which contains an activated carbon filter. And the reason for this is not just to try to get out smoke and stuff. That's easy because those are large particles. You can filter those. But you want to get out any highly reactive chemicals that are being released by the burning of so many synthetic products that you've got in a house today. So when you burn plastic, right? Or when you burn, you're not just talking about paper or wood, but when you're burning plastic, and when you might have some metals burning, and you might have, who knows what's in this building that's burning, you want to filter out as much of that as possible. Otherwise, that's going to get you too. So high-end gas masks contain those as well, activated carbon. You see them in some of the COVID masks that are being sold. They might have a little pocket that you could put a little filtration packet into that help them to remove those toxic chemicals. Does that make sense? Oh, it's the same thing. Here's another example. You'll see it. Activated charcoal is used. That's the same as the activated carbon. Is used if a person has swallowed something that's toxic, right? And instead of having them throw up, because sometimes that can make it worse, they'll have that person swallow activated charcoal. And so that charcoal or carbon can adsorb that damaging poison that was previously swallowed. That's another good example where you might see that. Okay, that is all that we've got for this lecture. So I'm going to pause the recording. We're going to take like 5 minutes again before we start in on our math and chemistry lecture here. So take 5 minutes. Yeah, it sticks. Oh, sorry. Answering the chat if I'm not paying attention. Adsorption means it sticks to it. It's exactly what it does. You have this activated carbon, activated charcoal, which basically means it's been treated to have a really large surface area. It looks like a sponge, but it's not squishy like a sponge. But it has a larger surface area, so something coming along just gets stuck to it. It does mean that after it's been used for a certain period of time, you have to change it, right? You'll have to replace it with a new activated carbon filter. Otherwise, it's not as effective. But yeah, it's exactly what it does. Okay, take 5, and we will come back and start in on math and chemistry.